Good day, everyone. I am Cesar Villanueva, and today, together with my groupmates Jamie Irasare, Ann Lumbreras, and Kim Manesca, we are going to discuss our project in Communications 2 regarding digital modulation. Digital modulation is a type of modulation wherein our carrier signal is modulated with a discrete signal. Discrete signals consist of bits or ones and zeros. Discrete signals are also known as square waves. In this project, we are going to discuss and show a simulation of the four types of digital modulation, which are the following: amplitude shift keying, frequency shift keying, phase shift keying, and quadrature amplitude modulation. Let us start with ASK or amplitude shift keying. Let's define first what is the amplitude of a wave. The amplitude of the wave is the distance from the center line to the top of the crest or to the bottom of the throat. In ASK, the main component of the signal that is being observed and altered is the amplitude. ASK is done by encoding the bit stream of our discrete signal in the amplitude of transmitted signal. In this example, we can see that the discrete signal or the blue signal, when modulated, will look like the red signal. When the beat is equal to 1, there will be an amplitude, while when the beat is equal to 0, there will be no amplitude. The difference between the amplitudes when the values of the beats are 1 and 0 should be very visible in order to decode or demodulate the signal properly. The demodulating signal should also be the same as the discrete signal to ensure the success of data transmission. In this project, we developed and designed a circuit that could depict the process of amplitude shift keying. This is the circuit design. We use clock voltage to simulate the square waves. In this circuit, we can see the modulating and the demodulating part. These are the signals taken from the oscilloscope. The orange signal is the carrier signal. The green signal is the discrete signal or modulating signal. The blue signal is the modulated signal for ASK, while the purple signal is the demodulating signal. As we can see in the blue signal, we have achieved the desired output for ASK, wherein there will only be an amplitude when the value of the bit stream is 1. We were also able to demodulate the modulated signal by bringing it back to the same form, which is as a discrete signal. We can see here that the purple and green signal are already the same, which means that the signal was demodulated properly. This is the video of the amplitude shift keying simulation. As we can see here, whenever the discrete signal or the green signal is 0, the modulated signal or the blue signal is flatline or it has no amplitude. While when it is 1, there is an amplitude in the modulating signal. In the modulator circuit, we can see that there is a clock voltage for the square waves, BC107 BP, BJT, and PN, 2N3906 BJT PNP, a 3-terminal operational amplifier, and resistors with 10 kiloohms and 1 kiloohms in value. While in the demodulator circuit, we also have a 3-terminal operational amplifier, 1N4007G diode, 3.15 kiloohms and 10 kiloohms resistor, and a capacitor with 100 millifarad and 100 picofarad. Why should we use amplitude shift keying? ASK is easy to implement, energy efficient, and requires a lower bandwidth, but it also has a higher error probability because there are cases where the difference in the amplitude of the modulating signal is not easily recognizable. That's why it's not also easily demodulated. That's all for amplitude shift keying.
Good day, everyone. The second digital modulation technique I'm going to discuss is frequency shift keying. I am Kim Nicole B. Malaska, and I'm going to talk about FSK. But let's define first what is frequency of a wave. The frequency of the wave is the number of waves that pass a fixed point in a given amount of time. Wave frequency can be measured by counting the number of crests or the high points of waves that pass the fixed point in 1 second or some other time period. The higher the number is, the greater the frequency of the wave. Now we are going to talk about frequency shift keying. Frequency shift keying is a type of digital modulation that conveys messages by shifting the carrier signal frequency in response to the modulation signal while maintaining the amplitude and pace constant. So from the word itself, frequency shift keying, therefore, there is a change in terms of frequency. There are two carrier signals used to produce the modulated output. These two carriers are called the mark frequency and the space frequency. In this picture, we have the message signal over here at the top, and the next is the carrier signal, which is the mark frequency that represents the logic 1, and the other carrier signal is the space frequency that represents the logic 0. Notice the big difference between these two carrier signals is that the mark frequency is always larger than the space frequency. Well, in this project, we develop and design a circuit that could depict the process of frequency shift keying. For the first part on the left side is the frequency shift keying modulator circuit, and on the right side is the demodulator circuit of the FSK. In the sample circuit given, a clock voltage having a pulse of 7 volt peak and 100 Hz is being connected to the circuit to the information signal. Two AC power sources such as B1 and B2 having the same value of amplitude, which is 7 volts, but different frequencies are being used. The V1 functions as the voltage through the collector of the transistor, and for the B2 is for the second transistor. The resulting output voltage of the two transistors is fed to the 741 operational amplifier that produces the FSK modulated signal. For the demodulation circuit on the right side, it consists of an RC filter and oscillator that helps to generate waveform to recovered information signal, same as the original input data to produce a demodulated output. These are the signals taken from the oscilloscope 1. The green color is the information signal. The orange signal is the space frequency connected to the V2. The pink signal is the mark frequency. The blue signal is the FSK modulated signal. As we can see in the picture, blue signal has achieved the desired output of FSK, wherein it is observed that during the binary state 1, the modulated output, or the color blue here, produces more signal frequency, while during binary state 0, the frequency of the modulated signal is same with the space frequency, as you notice. These are the signals taken from the oscilloscope 2. The green color is the information signal, the orange signal is the space frequency signal, the blue signal is FSK, the modulated signal, and the purple represents the demodulated output of the FSK. We can see that the violet and green signal are already the same, which means that the signal was demodulated properly. On this slide is a simulation of the modulation and demodulation circuit. First part is the modulation part, while the second part is the demodulation part. For the first part, it is connected to the modulation circuit, and the second part is connected to the demodulator circuit. Different waveforms are being generated by the entire circuit. So why frequency shift keying? Some of the advantages of FSK is that it supports a high data rate, it is useful in high frequency communications, it has low probability of error, it is easy to decode, it is used in low distance communication, and many more. The typical applications of FSK modulation is that it is used on voice grade lines, paging communication system, and even in coaxial cable based LAN. So that's it for the FSK or the frequency shift keying.
The third digital modulation technique I will be going to discuss is the PSK or phase shift keying. But first, let's talk about what is phase. Phase specifies the location or timing of a point within a wave cycle of a repetitive waveform. Next is phase shift keying. PSK or phase shift keying is a digital modulation system in the beginning phase of a carrier signal is changed or modulated. PSK is a code that is used to represent digital data such as binary digits 0 and 1. Also, it sends message signals by shifting the phase of the carrier signal in response to the modulation signal while maintaining a constant amplitude and frequency. There are two types of PSK. Depending upon the phases, the signals get shifted. First is the binary phase shift keying or BPSK. In this technique, the sine wave carrier takes two phase reversals such as 0 degrees and 180 degrees. Next is the quadrature phase shift keying or QPSK. This is the phase shift keying technique in which the sine wave carrier takes four phase reversals such as 0 degrees, 90 degrees, and 180 degrees, and 270 degrees. In this project, I used BPSK to simulate and present to you the waveforms that was generated. As you can see on the left side, the upper waveform is the input binary sequence or the modulating signal, while on the lower part is the BPSK modulated output signal. As you can see, when the binary sequence changes, there will be a 180-degree shift on the 0 volts. Next, now let's proceed to the process of modulation and demodulation. This is the circuit of the PSK. The carrier signal is configured to have a frequency of 5 kHz and an amplitude of 1 volts after constructing and modifying the circuit, while, while the modulating input is set to 500 Hz and 100 volts and connected to DC power of 5 volts. I used NPN and PNP transistor and a 3-terminal operational amplifier. The output of the modulator circuit will provide PSK based on the circuit. The amplitude and width of the modulated signal remains constant, while the phase shifts from high to low or binary bit 1 to 0 and vice versa. The modulator in this circuit uses an operational amplifier to create the sinusoidal modulating signal. Using the 4-channel oscilloscope, connect A on between DC power and R1, B on function generator, C on output of the op-amp on modulator, and D on output of the modulator on the circuit to observe and identify the PSK modulation and demodulation output. Next is the waveforms that are generated by the given circuit. The carrier signal is the orange, the modulating signal is the green, the PSK modulated signal is blue, and the demodulated signal is violet. The demodulated and modulated signals vary and distort when some of the components are changed. In these waveforms, the modulating signal is a binary sequence of 1 and 0, while while as you can see on the modulated signal, which is the PSK, there are phase shifts of 180 degrees and the binary sequence changes from 1 to 0 and from 0 to 1. Lastly, the demodulated signal is well retrieved by the circuit. On this slide is the simulation of the PSK, modulation and demodulation, as well as the waveforms generated by the entire circuit. Lastly, why phase shift keying? PSK is now widely used in a variety of radio communication systems. Well, it's especially well suited to the rapidly expanding field of data communication. PSK is a type of modulation that allows data to be transmitted on a radio more efficient more efficiently than FSK and ASK and other types of modulation. This method is broadly used for biometric wireless LAN along wireless communications like Bluetooth and RFID, local oscillator, and lastly, optical communications. And that's all for the phase shift keying.
Good morning, everyone. The last digital modulation technique that I will be discussing is the quadrature amplitude modulation, or QAM. What is quadrature amplitude modulation? It is a combination of amplitude and phase modulation which can provide high levels of spectrum usage efficiency. It is a type of digital modulation that can be used in both analog and digital modulation schemes. It has two carrier signals, the in-phase or I signal and the quadrature or Q signal. It has the same frequency, but quadrature is shifted by 90 degrees. It can be represented as sine wave and cosine wave. In this project, multi-sim software was used to create this QAM circuit to generate the or to get the desired output waveforms. The different components and the four-channel oscilloscope should be connected to its right place. The QAM modulator circuit is on the left side and the demodulator circuit is on the right side. The QAM modulator circuit is composed of clock voltage with a pulse of 5 volts and frequency of 1 kHz that serves as the input signal or modulating signal. The modulator circuit also uses two AC power. The first one has a value of 1 VRMS, 8 kHz with 0-degree phase shift, referred to as the in-phase wave, while the second one, called as the quadrature wave, has the same value of VRMS and frequency, but is shifted by 90 degrees with respect to each other. The op-amp and the voltage-controlled SPDT were used to add the two carrier signals, which results to QAM-modulated signal, while the QAM demodulator circuit, it uses 741 op-amp potentiometer with 20% rating to obtain the demodulated signal. These are the waveforms of the modulator circuit. The green signal is the input data or the modulating signal. The orange signal is the in-phase carrier signal. Light orange is the quadrature carrier signal. When these two carrier signals are multiplied, it will result to modulated signal, which is in blue. This is the waveform of the demodulator circuit. The first one is the modulating signal. The next one is the modulated signal. Then the purple signal is the demodulated signal. The QAM demodulator circuit uses the modulated signal as the input to get the QAM demodulated signal. Why should we use a quadrature amplitude modulation? It, support, it supports high data rates since it can carry a higher number of bits. It has high noise immunity resulting to a less noise interference during data transmission. Lastly, low probability of error values. For its application, it is used in wireless communication systems, cable television networks, cellular and digital platforms. That's all. Thank you for listening.